In this video, we're going to look at synthesis using the reactions from the prior chapters, linking them together to make complex molecules out of simpler molecules. We've already worked with reaction sequences in which we have a single step or possibly two steps linked together. In this particular transformation, we have an alkyl halide of 6 carbons, and at the end we have halohydrin of 6 carbons. We've either functionalized the 1,2 position, and that often happens through elimination reactions. That's what actually is indicated here over the arrow. In step 1 of the synthesis, we make an alkene that is on the end. So we use a bulky base, and the base is strong, so we get an E2 elimination without any rearrangement. We then create an alkene that then can brominate with an OH using the halohydrin reaction. Often we have this 1,2 over the arrow indicating that we actually do the reactions in order. We start with the elimination reaction, and after a while we would add the bromine and water to the mixture. Sometimes we actually isolate the alkene in between and then do the second step. The other thing this is telling us is about reagents and solvents or conditions. Usually the reagent is the first thing listed, or if there's more than one reagent, those are the first things listed. And after the slash is the solvent or heat or other reaction conditions. And for the second one, water plays a role as both a nucleophile and a solvent. Here we have a larger functional group reaction sequence in which we start with 6 carbons, end up with 8 carbons, and change functional groups along the way. If you look carefully, the functionality of the original starting alkene is this double bond on the end. And with a little bit of imagination, you can see that that's probably the 6 carbons that are right here, farther on. That is, these 6 carbons are still around where the functionality is. In the process, in order to make 8 carbons, we had to have made 2 carbon-carbon bonds. To do this particular sequence, we first create an epoxide with MCPBA. Then we make our first carbon-carbon bond by doing an SN2 reaction on the epoxide and protonating to make this alcohol. Then we have to convert this alcohol into a nitrile group by first making the OH into a good leaving group, followed by an SN2 reaction to replace it with the nitrile. But often when we do synthesis, we have a goal in mind, a target molecule, and we want to figure out how to make it. We want to make it from pieces that we can buy inexpensively or that we have available in our stockroom. So a typical synthesis problem might be to make this particular alkyne, which has a total of 6 carbons, out of pieces that have 3 carbons or fewer. Doing this, we are going to use some of our carbon-carbon bond forming reactions that are included at the ends of the chapters. For example, one of our carbon-carbon bond forming reactions is to take an alkyne, remove a terminal hydrogen, do an SN2 reaction, and make a new carbon-carbon bond. And we can use that in our synthesis. So our process of looking at this problem, we start with our product and we imagine what bonds could have been made. This funny arrow here, this open arrow, is called a retrosynthetic arrow. And this whole process of thinking backwards about a reaction is called a retrosynthesis. So we can imagine that the 3,4 bond could have been made reactions from a 2-carbon piece and a 4-carbon piece. This is what we call retrosynthetic analysis. This piece also has more than 3 carbon atoms, but it has an ether in it, and we know we can make ethers through Williamson ether synthesis. So again, thinking backwards, we can imagine making the bond right here, that carbon-carbon bond, if we had a halide on this end and a nucleophile on the other end. Or we could have done it in reverse, where this was the nucleophile and methyl was the alkyl halide. So then when we put these pieces together, we find that we can start with a 3-bromopropyne, treat it with sodium methoxide, do an SN2 reaction to make the ether-containing alkyne with 4 carbons, and then remove the hydrogen on the end and do an SN2 reaction to extend it to 6 carbons. Of course, there's more than one way we could have broken this particular piece up. We could have made a different carbon-carbon bond. For example, we could have imagined using the terminal alkyne reaction to make the 1,2 bond. which would have given us this piece plus an alkyl halide. And then we could have imagined the 3,4 bond also being broken through another terminal alkyne reaction. So another synthetic sequence that would work for this is to start with ethine, treat it with sodium hydride, followed by ethyl bromide to make a 4-carbon alkyne, treating it again with sodium hydride, and then with this bromo ether to make the final product. In this synthesis, we don't have to do a Williamson ether synthesis. We make 2 carbon-carbon bonds instead. One of the challenging parts of putting reactions together and predicting what's going to happen is that we have a number of synthetic traps, things that happen that we may not expect from doing our retrosynthetic analysis. One of the most common synthetic traps is when you have more than one functional group and reaction takes place at a position you didn't expect. In this particular case, if we were using a terminal alkyne and an OH, we would have found that the terminal alkyne is going to protonate from the OH much faster than it's going to displace the bromide. So instead of getting the SN2 reaction we wanted to make a new carbon-carbon bond, we would get an acid-base reaction. Anytime you have a compound with more than one functional group, you have to consider this particular synthetic trap. Another synthetic trap arises when you try to figure out how to convert from one to the other. For example, here we have a bromide, and we might say, well, we could have made that by an addition across this pi bond. But when you look at how the reaction goes forward, you'll find that the HBr adds in a Markovnikov fashion, and it's going to end up in the wrong place. In order to make the bromide appear in the right place, we could do hydroboration oxidation to make the corresponding alcohol, followed by replacing the OH with the PBr3. So we can get around this particular synthetic trap of the wrong regiochemistry by using an alternative pathway. So the synthetic traps, to summarize the ones you might see, if you have a multifunctional compound, you can react at the wrong site. Often acid-base reactions are the undesired reaction. You can also have the wrong regioselectivity, like we saw in the second example, Markovnikov addition versus anti-Markovnikov, or Zaitsev versus Hoffman elimination. A third synthetic trap might be to create the wrong stereochemistry. For example, you have to remember that SN2 gives you inversion, so if you want a particular chirality center, you need to start with the right chirality center. Also, addition reactions, some of them give exclusively syn or anti products after conversion, and you want to make sure you start with the right alkene to give you the right stereochemistry of the product. And finally, certain reactions just can't happen, even if you can predict them on paper. One classic example is to try to do an SN2 reaction at a center that is too hindered. But when you do a number of reactions in order, as you probably have figured out already from lab, each reaction gives you less than 100% yield. A linear synthesis is less efficient than a convergent synthesis, because if you were to get exactly 80% yield on every step, we would find that a linear synthesis loses material at every step. And so if we were to do a linear synthesis of 8 steps with an 80% yield on each step, we'd find we only get 21% yield overall. To get this number, by the way, you multiply 0.8 times 0.8 times 0.8 times 0.8, 0.8, because each time you're getting 80% of what you had before. On a convergent synthesis, we can get a somewhat higher yield. If we have an 8-step synthesis by combining branches, each of which has 80% yield, we have 0.8 times 0.8 times 0.8, and then a final multiplying by 0.8, we get 41% yield. In the laboratory, you might note that we are doing a convergent synthesis. We're doing 2 branches, each of which will have its own percent yield, and then the final percent yield. This leads to a greater amount of product than if we had all those steps in a linear pathway.